certain types of statistical tests or other kinds of types of manipulations of data where they make some types of assessments or predictions. Well, we're talking about that stuff today, and one of those tests is going to be a t-test, which is actually quite interesting, which is in our slides you see on our screen right here. And then we're going to move into other kinds of tests, which are called regression tests. And so that's the stuff that is in the slides that you would have also found in your that you just pulled over. Let me just go ahead and check my notes here. Nothing too crazy that I always say. Okay, there we go. So yeah, so let's go back to let's go to these slides here. Basic stats, hopefully you can see them on the screen. There you are. One thing we did cover last time, though, please don't forget, are functions. Functions are actually quite useful when it comes to doing repetitive work over and over and over again. These are ways of kind of like putting code into a certain part of your program, and then if you run that same code like repeatedly, why not just make a function out of it? And so you can just keep on just calling the same function, and then that function will do exactly everything you ask it to do in exactly the same way. And so we talked about functions here where we have a function that's called the sum of the squares, and we have to first of all define it as a variable, and then we have to tell R that it's not just a variable, but rather it's a function, and it has two different variables or two different parameters that go in. And then inside these curly brackets here, if you're familiar with Java programming, then these curly brackets will be nothing new. But if you're not, what happens here is that this stuff inside all the code that we have inside these two brackets, rather this right here, this is the actual meat of the function. That means this is what the function will actually do. And so it's actually quite important to use. What's my slides here? Where are they? Oops, there we go. I minimized my browser by mistake. Anyway, but it's actually quite important though to use functions in your code, because many of the times when we run statistical tests, I think that, for instance, there's one of the right here, for instance, this could be a statistical test that we may run hundreds of times during some kind of an analysis. This particular function plots an x and a y in a red color. So basically, it makes a series of points for your x and y. It's a Cartesian type of plot here, where you have an x and y that gives you a point. The x is on the x-axis, and the y is on the vertical y-axis, and this just puts a point. But this point is actually colored in red. And so the reason why I'm talking about this here is because you might be running some kind of an analysis in your work where you're producing seemingly hundreds of plots. After all, plots are how we're going to be using or how we're going to be visualizing things that happen in our data. And so you need to be able to kind of run these things over and over and over again. Anyway, if you have seen functions before and you already recognize that they are important for different reasons, then I don't mean to undermine your intelligence by just talking again about these things. But really, this discussion is designed for those people perhaps who haven't seen functions before. So anyway, but they are helpful though. And for instance, to call this function, you can just go ahead and use this 2 and 4. And what this thing does is it finds your 2 value on the x-axis, and it finds the number 4 value on the y-axis, and it puts up a red point. So this could be very, very handy if you have seemingly thousands and thousands of points. Rather than just making a plot for each of those points, why not make a function and then just call this function each time you need to make a point? Anyhow, this, by the way, don't forget this. This is actually if you're defining an array of points from 2 until 10, and this is also your array of y points from 2 until 10. Again, you can create a whole series of plots of points. I'm not going to worry about putting this into RStudio right now. I think that we did that before, but I do invite you though to play with these functions, because they are rather. I mean, they are very useful. Anyway, I'm going to move now to. This is another function, by the way, where we have a conditional. So, for instance, now I can take in my incoming number, my argument, and then I can say, well, is this number in is it greater than or equal to 5? And if that is the case, then do this. So that means really whatever code you have inside these brackets is what happens when it's true that the argument number that comes into the function is greater than or equal to 5. However, if this is not true, where that means that this number is not greater than or 5, means it's less than 5, then you print up this line here. You're doing this thing here. So it's either your function goes, oops, either your function goes, it checks this thing if that's true, and it prints this, and if that's not true, then it will go here. So it's one or the other, either greater than 5, or it's greater than or equal to 5, or it's less than 5. And so that's kind of how these functions work. It's all just conditional statements. We talked about these medians, which is like the middle number of your data. And so, for instance, you might need to, it's not the middle value, but it's like if you have all of your numbers sorted in a big array, it's like you're able to find the middle number. And so you can get an idea about what the numbers look like in the very middle of your thread. Now, remember where we're going with this. You're probably thinking, why do we care about these words? Why do we need these statistics? Well, remember, what we're doing is we're trying to define a kind of a language, if you will, so that you can just go and you can just tell people, this is my median, this is my mean, or this is my other, these are my quantiles, or these are my other things. And we have quantiles here. But you're saying that this is what the data looks like, or these are the numbers to measure certain types of data, so that in the mind's eye of the person that you're speaking to, they know what the data is, what it looks like, what the plot would look like if they were to plot this. And so we're just creating a language to describe how the data looks if it were to be plotted. Remember these quantiles? The quantiles, we're talking about where the data is actually falling. Most of your data will be falling between quantile 1 and quantile 3 in this blue section. That's like your 50%. And so you expect most of your data to fall in that area there if this is like a normal distributed data set. Now, if you have some kind of data where it's skewed to the left or to the right, then you'd expect it to be happening before the Q1 or after the Q3 marker there. And what that's suggesting is that you can say that there's something going on with this data where it's not falling near where the median is, but rather it's falling before these in the outskirts of your distribution. Anyway, but the thing is though that if I can give you my quantile values, as I would right here, then in your mind's eye, as I keep saying, then you have an idea about where those values are falling, like how much of the values are falling. And so, for instance, in this particular in this data spread that we have here in the data set, I should call it, it's saying that in my graphic below, it says my first quantile is 7.25. That says to me that that 25% of my data is falling before that point. And then if I look at my third quantile, 14.50, 14.50 is saying that that's about what here, I guess. That's saying that 25% of my data is falling after that point, whereas half of my data is actually falling here. So again, if someone says to you, tell me what the quantiles are of this data set, and you tell them, well, the first quantile is 7.25 and the third is 14.50, then if you have an idea about how the numbers look on paper here, then you also have an idea about how they look when they're plotted. And so this is really where this is all going. It's just, for instance, figuring out how to describe the data in quarters. So anyway, you have some information here that gives you there's some reading information that you can use to kind of as you're looking over your notes here. The second quantile, by the way, the second quantile is the median, which is like the middle point of your data. It's the absolute middle. So that's why they don't usually mention in this graphic here, they don't say the second quantile, but they just say median. Well, that's what the median is. It's your second quantile. So I don't know why they don't just call it quantile 2 or something. It'd be easier that way. It just does. Anyhow, then we discussed this function here called summary. Summary is actually how you get this information quickly. Now you're probably thinking, what's the big deal about summary? Why would I need to have a slide about summary? Well, because summary actually does all this work for you, and it does it very quickly. If you were writing code yourself to actually compute these things, then this might be, seemingly a page of code to make any of this stuff happen. Whereas for this, it's just a built-in command that you just call, and then it does everything for you. So it's actually a built-in function, which is very, very similar, if you will. It's a function that's similar to this. It's just that we don't see the code. I mean, we can if we want, but it's basically just a function that does this, where instead of giving it X, Y, and Z, what you're doing is you're giving it the data sets, and then inside that summary command here, there's code where this block would be that gives you the quantiles and the medians and even the mean, which is right here. Remember, the mean is the average. Then you have your min and your max values too. Okay, so that's all very, very cool. Now we're talking about, for instance, the I guess the correlation. Now this is actually getting kind of, this is actually an important area because I'd say a lot of the data analytics papers that you may read in the news talk about correlations between different kinds of data, I guess, different types of data. For instance, they might say that there's a high correlation between people who don't wear masks and getting infected with COVID. They're saying that as one set of numbers goes up, as the measurements of people not wearing masks goes up, then so does the measurements of people who get infected with COVID. And so you see that coming out seemingly all the time in the news, where you have these correlations where as one thing is happening, something else is also happening. In this case here, I have hours spent studying. That's one piece of data. That's something the more time you spend studying gives you better grades. And so the more time that you have there studying, the better your grades are. Now, I should say one more thing before I finish with the correlation idea, and that is that the x and y axes of your plots have to be things that you can measure. You have to be able to measure this stuff. You have to be able to say that hours spent studying. I mean, look at these variables, they call them now. We're going to call them variables. But look at the variable of hours spent studying. That's like something you can measure. I can actually say that today I spent 3 hours studying for this test. Yesterday I spent another 3 hours, and the day before I spent 2 or something. But this is actually something that I can say this is a number which has a value. And these are my grades on the other side here. So in this sense right here, I would say all these points, just the way I'd read this. Let's see, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I see 10 different points. That might suggest to me 10 different grades, where, for instance, I'm figuring out how many hours I spent studying for a particular test, and my grades are the grade that I got for that. So let's just say that I'm just going to choose any old point here. So I'll say that the fourth point, the longer, wherever it is, any point, if I can figure out what that x value is, then that's the amount of time that I spent studying for something. That's my x value. And then my y value would be the grade that I got for that. I might find, for instance, as the as the values of x are low, that means as I spend like maybe half an hour to an hour studying for a test, you can see that my grade isn't that high. But the more time that I do spending, like as I get to this end over here, the more time I spend studying, then the higher my grades are in general for uh, my tests that I'm taking here. So you kind of get the idea, but each point here is an x and a y, and the x is going to be the time, and the y is spent, and the y is the grade that you got on that particular test. So I think that might help to clear things up. This is what they call a positive correlation, whereas one thing is going up, the other thing is also going up. Now, this is a negative correlation between time spent away from studying and interest level in classes. And so what this is saying is that the less time I spend, or as the amount of time that I'm spending doing other things increases, in other words, the time spent away from studying, as that number goes up, then my overall interest in my classes goes down. So that's true. And again, each of these points is going to be a number of time, an amount of time, and then the interest level in that class. And you can see that it's going down, which means it's a negative correlation. This is a no correlation, which means that there's nothing going on. It doesn't matter how many times, how much data you plot here, you don't get a distinguishable line. The amount of time talking about Sherlock Holmes and the level of programming skill in R seem to have no response to each other. In other words, one thing is not influencing another. So this is actually quite an important piece of coding that you have here. This is actually a piece of analysis that you have, because if you're trying to make the point that the more times this thing happens, then the more times another thing happens. If you say that if you're trying to form that argument, then you have now the tool to make that argument happen with correlation. Um, and for instance, as we were in the theme of what we were talking about before, where we're actually putting numbers on things, or finding a way to actually quickly tell somebody what the correlations look like without having to make a plot like this, I could just say that this plot here has a correlation of 0. And so, for instance, we have this number system. So a correlation of 1 indicates a perfect positive correlation where one thing is correlating with itself. -1 means it's a negative correlation. And 0 indicates that there is no interaction between these two variables. Just remember, though, that when you're talking about correlations, you're going between -1 and 1. And so, I've actually saw the news a couple of weeks ago. Somebody said there was like I don't know, a correlation of like 1,000%. And what are they talking about? 1,000% correlation between something. And while I got it that they were saying that there's a high correlation between two different data sets, that is actually mathematically wrong. You cannot say that there's 1,000%. You're talking about not percentages, but you're giving actually scores. You don't go home and watch a basketball game and say, "Oh yeah, the score was 1,000%. It was just incredible. My gosh," because people will think that you're just just crazy. Like, what are you talking about? 1,000%? Oh yes, 1,000% score. It means nothing. You get the idea that one team may have won or didn't win, but still, you need to kind of come up with the right kind of grammar or the right language to describe what the score is really. Okay, so these are different correlations we talked about last time, where you can kind of get an idea that when you plot the plots, when you put the numbers out on plots here, it doesn't always come out to be perfect looking correlation, but you get an idea by looking at the points, and in this case, looking at the R value. I don't like that R. I don't like calling it R. Sometimes I do, but I would call it C for correlation. But R in this case is what they're calling the correlation value. So for instance, in the upper right-hand side, where my R is equal to 0.96, we get it that there's a correlation between the X and the Y. As one thing is going up, the Y is also going up. And the value of 0.96 is a score on how those two things are correlated. Going to the the left, upper left here, upper left, where R is equal to 0.34, it's not very much. It's not a huge correlation. It's pretty close to, I mean, it's greater than 0, but it's not such a great correlation. It's not very convincing that these two things are actually and somehow connected. They're somehow connected to each other. In fact, if I saw these numbers, I could be also convinced that it's just random. I'm hoping also, though, that as you're looking at these particular points here, you're getting the idea that sometimes it isn't good enough just to show a few points, but you need like a bunch of data, like a whole bunch of data. The more data you have for your argument, the better. The more people you ask about a movie, if you're thinking about going out to see a movie, but you're not quite sure whether that's the movie you want to see or whether you want to spend $7 or whatever it is, $8 now in seeing a movie, you might ask a whole bunch of people. But if you just ask your roommate and say, "How did you like this movie?" And they said, "Oh, it was not so great. It was a silly film. I didn't like it so much." Then you might think, well, surely there's got to be something more to this movie than that. And so you may ask more people. And so the more people you ask, the better your feeling is or your understanding is of the goodness of that movie. This is also called crowdsourcing, where the more people you ask, the more data points you collect, the better. The more information you get, the better you are. And so here, for instance, these points with such a low correlation of 0.34, if someone was trying to connect to me or trying to convey to me the notion that the advertising expenditure and sales were somehow making there's a positive correlation, numerically there is a positive correlation at 0.34, but I'm not convinced that it's really a great correlation. It just appears to be maybe a random correlation. And the same thing goes for the below the correlation of R is equal to 0.72, where yeah, I can kind of make a line, but again, there's not very many points there, so it's actually kind of difficult to see that there really is a strong correlation. In other words, if you're looking at a plot like this, where you have these points, I mean, I guess this could be arguably a good trend here, but as a data scientist, though, you should always be asking yourself, Is there more data that I could use to get more information out of this thing? I mean, otherwise, it looks like these points are working out quite nicely. There's a negative correlation. But for instance, if I had like hundreds of thousands, perhaps more points, if I could get those, would I still see the same correlation, or would it look like this? So it's hard to say. So what I'm trying to say is the more data you have, the better. And so in these correlations, in these graphics, each little speck that you can see, each little pixel actually represents a piece of data. It's a data point. And so you can see that the data scientists who put this particular or these plots together actually used many, 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 many points to make their many data points to make their case understood. In fact, if you look at their I'm looking at the second over from the left, Pearson's equal to R 0.8. I mean, there's a lot of points there, but in general, I can see a very pronounced positive correlation. And so I guess what I'm trying to say is that the more data you have, the better. Then we have some code that we looked at here for correlations. Now, this is where we kind of began to break up last time, where we were talking about the variance. Now, the variance is actually another very important piece of statistics, and that is that I know that it's kind of absurd to say the expected amount of information here, the expected placement of your data. I mean, how can you expect to find any proper placing or placement for your data? But what they mean by that is that it's the mean. So if you take all the points that you have and you put them on your plot them out, and you compute the mean, or like the smooth line, the mean smooth line that would somehow skewer all those points and go right through the middle. In other words, you can just look at the line now without having to look at the points. Your variance is going to be the average, if you will, of all these little arrows, the little skinny black arrows that we can see that point out from the mean arrow, but it'll be all those those averages there. And so what you're saying is this is a measurement of how far the points are falling from where the statistical mean would be of those points. And so in this case here, the variance is 0.93 for these numbers. And so you're saying that when I calculated where these numbers should be according to their means, then this is my average value about how far away those numbers. Or sorry, this isn't that. It's like the difference, I guess, or it's the value where those points actually did fall. Then we move into the standard deviation. That's really why we care about the variance, though, because it gives us the standard deviation. Standard deviation is the square root of that value of the variance. So in this case here, I plugged in my data. I got this variance value of 9.3. Exciting, but actually to make any use out of this, I mean, for my work, I mean, anyway, your work may be different, but I usually use the standard deviation. The standard deviation says just take that variance value and take the square root. And so here we find this value of 3.1. So what does that actually mean in terms of graphical values here? If I were to plot these points, well, you can think of your standard deviation as when the value is a very small value. That's what we see on the screen here in red. That means that the points are really kind of scattered close to where the mean line would be. In other words, everything's really kind of like, it's a sharp point, in other words. It's a very sharp point where the points are all kind of like gathered together around that mean. There isn't much play in the points. They're all more or less in the same area. But more importantly, in your mind's eye, you can see that it's not spread out. Small standard deviation suggests that the numbers are all kind of packed together near the mean. Whereas a large standard deviation, the big numbers, as numbers get bigger, it suggests that the data sets are more spread out. There's like, there's much more difference, if you will, between the small values and the big values. In the red version, for instance, of the small standard deviation, I see that my x values begin at x equals 60, and they end at about x equals 120. That means that all my values are snug between 60 and 120. Whereas for my larger standard deviation, my values for x are spread out throughout the entire plot. You can think of this in terms of small and skinny or large and lazy. Large and lazy is kind of like the points are just kind of like throwing themselves forever. Just like kind of flat. It's like large standard deviations. Standard deviations here suggests that the numbers are just spread out all over the x-axis, whereas small standard deviations suggest the numbers are tightly packed together. Now, you might be at this point wondering, I have some numbers here. You might be, here we are, standard deviation here. How do you remember this? Here, spread out. If it's a high standard deviation here, large and lazy, it means spread out. But you might be wondering though, why would I care about these? Why would I care about the standard deviation? In fact, when I first saw these standard deviations, when I took a probability and stat course, when I was when I was your age, I hate to say that, but you might care about that because imagine, for instance, this is the number of supposing you have a nonprofit business, and these are the donations that people are giving you on your website. X-axis represents perhaps the time that people are giving donations, and the Y perhaps is the amount of money that people are giving you. But you might want to figure out, like, when is the best time to start asking people for money? In this case, when I plot the data down, I'll find out that most people, and if I'm looking at the red, most people are giving money around this time zone, 90 to 100, wherever middle of the day. And it seems like that's when they're giving out most of their money, my nonprofit organization. And so that would suggest to me that that's a good time to start putting out more and more, maybe ads or things for people to click on so that they can get to my nonprofit and start giving out money. Whereas, for instance, if I plot my data about when people are giving money and how much they're giving, and I'm using the large, and I find out it's a large standard deviation, this would suggest to me that it really doesn't matter when in the day I put up my ads. People are more likely to give out their money in the middle of the day, but it doesn't stop them because some people give out money at night or in the morning. And so you would want to use a kind of a plot like this or a standard deviation to figure out when is the best time. Your x is equal to time and your y is equal to the amount of money that people give. When is the best time to start asking people? I know that's a kind of a cut and dry type of example here. There's other examples that perhaps you can come up with yourselves, like when is like another question of when something should happen. But again, it's a standard deviation type of problem here that you can solve just by looking at the plot, or just by looking at the numbers and say, okay, well, I see that my standard deviation is 7.9 in the first one here. This 7.9 could, in this case, the x-axis here or the x-axis is talking about the score, and the y is talking about the number of people who reach that score. And so if I say that the standard deviation is 7.9, I can say that most people achieve high points or high scores around the 7.9 marker, which means that that's kind of like where I'm expecting. If I'm designing in this case, this is a test here, the IQ verbal and the IQ math and the IQ spatial. These are all tests, and these results are determining where my test takers are actually, where their grades are actually falling. In this case here, I'm finding that most people are taking their verbal tests and they're doing well around 7.9. With a frequency, that means that more people are kind of like gathering in the middle there, around 7.9. My math seems to be a larger standard deviation where things are more spread out, which means there's more variability perhaps between how people do on the math test. And if I see the IQ spatial, I can see that there's a lot of variability here. The SD equal to 31.6, that's where I'm expecting things to, that's where I'm expecting people to, or the, or that's just saying that my standard deviation is more spread out. And so I guess you could say that 31.6 is the, I don't know, just the measurement of how spread out people are doing. Maybe they're not doing, there's this, the scores are so diverse that it's hard to kind of see them all in one place in the plot. Whereas in the verbal, the scores, the standard deviation is low. And so therefore it's kind of like, actually, sorry, so the 7.9 here is saying that the scores are more likely to be kind of like gathered together. So most people who are taking this test are actually getting around 90, I guess, whatever the x-axis is here, 90% or 90 of the questions, 90 out of 200 questions correct or something. I'm not really sure exactly what the x-axis here is. But the frequency, though, suggests that most people are actually doing very similar work, and all their results are happening between the 80 and the 120. Anyway, the long story short is, I guess until I really know what these variables are, it's hard to really interpret them. But the long story short is that when you're looking at these standard deviation values here, the larger they are, the more spread out the data, and the smaller the score is, then the more kind of compact the data is. So that means the closer the data is to the mean when it's small, and if it's a large standard deviation, then the further to from the mean the points tend to be found. So anyway, I know this is seems like I'm going around in circles here. These plots, unless I know what the variables really mean, it's hard to really understand like what the points are. There's no information about what the x-axis is. It's hard to tell exactly what's going on. But I do read them though as that the standard deviations suggest that the number suggests how close everyone is falling to the mean. Okay, now I wanted just to show some. I will do this code here. I think this is actually kind of interesting here. Um, we're going to use this library here called Tibble. So if you come with me to the, where can we go? Oops, this here. Give me my thing. Ah, I'm trying to find my trying to find my. There we are. Got it. Okay. I had to load my R Studio. This is code that I think we did last time. I think, what is this here? The date. Yeah, this is last time code. So what I'm going to do is I'm going to just start building onto this. This is my focus from the 22nd of October, so that's last week sometime. So I'll just put this 22nd October. I'm just writing this down for my own information here, otherwise I'll forget exactly when I put this code together. But what I'm going to do is I've just copied this information from these slides here, copy that over, and with some luck, everything will look relatively okay. It doesn't look okay, so what I have to do now is I have to go through and make my text look like this. So let me just go back and do something here. So I have data people, I believe that's it. Okay, now that I get the color coding here, it makes me think it actually worked out okay. I'm going to run this stuff. I know that the code down here doesn't look beautiful, but I think though that if you go ahead and hit, if you actually view the information here, I've just created this data here called data people. So if I view data people, then there we are. So that's what. Okay, so what do I have here is the eye color, the height, weight, and age. Imagine, for instance, that I'm that I'm collecting some kind of information on people or something else. Maybe they're what I'm looking at, but I have actual. And you'll notice that the things that I have in my table are actually things that can be measured. We have eye color, just blue and brown, I guess. Then we have the height, the weight, and the age. Now, if I type in, for instance, names, data people. Well, I guess you can see what the columns are here. So if you needed to get to those columns, you could do that without having to go through and looking at this table. But now what we're going to do is come back to the slides with me. What we're going to do now is we're going to look at these slides and we're going to calculate the BMI, or the body mass index, and we're going to look at some statistics with BMI. So the code that does that looks actually kind of messy. But remember, the BMI is you're taking the height, and in this case, you're dividing it by the weight squared. And so if you take someone's height and you divide it into their weight squared, or their weight times weight, then you can get this BMI. Now, whether or not you're convinced that the BMI is actually an accurate measurement of any kind of health, that is completely up to you. I have read papers on both sides of the issue saying that yes, the BMI is a good thing to have, and other papers actually from some very reputable medical doctors and some athletics scientists, data scientists in athletics, who are saying that actually the BMI actually isn't a very good indication of anything. So the jury seems to be out, as it always is. Anyway, but what I've done though is, I'll just take you through it. What I've done is I've taken the data set people that I've just created, or the data people, which is this table that we have here. Then what I've done is I use this part here and then. And by the way, before you, if you run this and it doesn't work, please do not forget to load your libraries. This dplyr library will has, I mean, there's a lot of overlap between dplyr and tidyverse, but that will allow you to use these. Now these, remember what those are? It's like you're piping information from one thing to the next. And you can think of them in terms of the words and then. So I'll take people data, which is my table of information, and then what I'm going to do is I will select the eye color, the height, and the weight. That means just grab those rows for which the eye color, height, and weight is there. Um, and then filter out the eye color, which is blue, and then create a, this mutate makes another column. So create a column called BMI, which is equal to the weight, which is this, over the height squared, which is that. And then compute for me the summary of that. Let me just show you something else here. I had a couple of questions over the last week about these and thens. Is that you can, if you find that stringing things along like this is just too tiresome, then what you can do is you can create like another data set here. I'll call it data people. I don't know, BMI. Let's call it BMI. BMI. This will work, and if I run this like that, I don't need this information. Here, I can get rid of that. But you can see though that what I've done is I've created a data set called BMI from this data set data people, which was this table that we just put in there. And in there, I've selected some data. Actually, I have to select some rows in some way. So I'm selecting the rows, which are just eye color, height, and weight, and I'm leaving behind the age column. I don't need age. That's why I have this select here. I don't need age. I just need BMI. So if I go ahead and click on my data, you can see that what I get is eye color, which is something I selected, height, which is something I selected, and then weight, which is the last thing I selected. This BMI, this is what I calculated, and that was our 1.8 in this case here, 1.8 over 110 times 110, and that math gives me this value here. So now I've been able to kind of create this new column of data, which is the BMI, and it was relatively simple to do. Now, the next thing in this long code that I just gave you, what this thing does here is it's going to like compute this summary. So I'm going to just leave this line alone for a second here, and I'm going to go back to my data set here, and what I'm going to do is I wonder if I can just go ahead and put in, just put this here, and then it'll and see what comes from that. So there we go. So now I'm able to kind of connect to my, I'll get some BMI information, and hopefully, if I go ahead and run the other line of code, it's the same information. So what I'm trying to say is that when you look at your slides, like here, and you're seeing a whole line of just unintelligible stuff, don't freak out. Don't worry about that. Just go through and kind of pick out piece by piece what's going on, what's happening in your code. And once you have that information, then you can, once you understand like what's actually happening line by line here, then you can take things out, just as I've done here, whatever that was. You can kind of take things apart and then make things a little more easy to follow. In fact, sometimes this is the better way of doing it, because if you're working with somebody who doesn't seem to be very experienced with R, maybe you'd like to share code with them that looks like this so that they're more likely to follow it. So all of these things don't have to be piped. You can always create variables for each step of the way and then just keep modifying those variables. And then at the very, very end, you have a final variable that you've created from the other variables. You can use that to create your summary. Anyway, I'm not telling you how to compute. I would say just choose the method for you that feels easiest, and then you'll be fine. Anyway, back to the message here. So now we've used the summary command here, and summary, what it's done is it has determined for us. Oops. It's determined for us the mins, the maximums, the first and third quantile, the medians and the medians and mean of the height, weight, and BMI data. And really, it didn't take us much effort to do that, which is actually quite astonishing if you think about how much work actually goes in making these things happen. But now, for instance, if you're writing a paper on BMI and those kinds of things, you can include these numbers in your paper, in your text, and the readers, if they know about statistics, then they should be able to kind of like close their eyes and kind of visualize the data in front of them without having to see the plot. Of course, the plot always helps. So I'm not telling you to like kind of forego the plot every time, but sometimes though you can save some space in your work just by talking about the actual numbers. Now, what I want to do with as my next step here is to actually put the plot up there. I think that the plots are helpful, and so we'll go ahead and I'll just copy this back with me. There we are, and I'm going to put this plot down here, and hopefully this will do it. But I need to find ggplot. Before I can do that, one thing that's on my slides is I have to put library tidy verse. Oops, tidy verse. There we go. I run that, then I run this. I should have put that in the slides. Tidy verse. Anyhow, so you have this beautiful plot, and it even has it has a smooth line, which is quite nice, which means that really it's telling you like where the expected placement is for some of these things. And so if you're looking at the plot here, you'll see that this blue line is the expected area where these points are supposed to show up. You also have color in here, although the color isn't really all that powerful or that meaningful because we only have just a few points actually, and so it's kind of hard to see the differences in the colors. But you do have this shading here, which is your 95% confidence level. So we're saying that I know with some certainty where the points are, if there are more points, where they would fall, because I know where these points are. So for instance, here on the plot between 150 and 175, the plots, the confidence zone is kind of zeroed in between 1.8 and 2.0. That's saying that if I had more data, then I would expect to find it there if it's in keeping with this data. However, if I have more data and I'm plotting this here between 125 and 150, this is saying that I don't have enough information from my points to know where those new points would land, because I have no way of assessing where extra data would go. Okay, and you can see this all here. Let's see. Let's go back to our slides. What else is there? Oh yes. Oh yes. So now I'm going to copy this and see what this information is going to tell me. Come back with me. There we go. I'll just paste this here. Now, what this is doing is, this is something we haven't seen before. We're using something called the facet wrap, which is actually a very powerful tool, which I invite you to use when you're comparing two different types of data or two different plots. What this is saying is that what it does, it creates these two plots side by side, so you can actually do some kind of an experiment. You can actually do a comparison. And what we can see now is, in fact, I can just move some of this stuff around so that it's a little more. Like that. And so what this is saying here is that I have my first plot is where I'm looking at the where does it say here? Here we are, facet wrap by eye color. So it's they actually say we're aggregating our data according to eye color. And so if you go to the data people, or rather, which I'm looking at here, data people. If I'm looking at this data people set here, you can see that eye color it's basically a binary, variable here. It's your variable that's either blue or it's brown. It's nothing else. And so it's so what you're saying is you can break the data down by these two either brown or blue markers. And so going back here, this is saying prepare these two plots here, but actually break them down according to the eye color. Now you could try this. I mean, you could change things around here, and it's a categorical. You could change it around where you're not using a categorical variable. But I think you'll get into some trouble here. But what I will try though is if you look at height, height could be considered categorical because I see that there's 1.8, 1.9, 1.7. Either it's 1.8, 1.9, or 1.7. And so that could also be a kind of a category. So let me just go ahead and try that and see what my two different plots look like. We'll go back in a second and see what those plots are actually talking about. That was the height with it. And so there we are. So now I have been able to aggregate my data according to the height. Where if your height is 1.7, then you fall into this plot on the far left. The middle plot is 1.8, and the far right is 1.9. And here you could argue that the points are actually kind of meaningless because where you see the points actually showing on the x-axis. So for instance, in the far left, you see 1 point, which is at the y equals 1.7. Remember that the y-axis is height. And so we're breaking up our points according to their height, but actually we're not learning anything new because the points are already being described as 1.7, 1.8, and 1.9. And now we're just separating those plots out. And so actually this plot here is not helpful. Let's say here, not helpful. Whereas this plot up here, I would say is kind of helpful. And so what we're seeing now is the kind of the numbers as they move around. So for people who have blue eyes, their weight seems to be all over the place. That means the data set is suggesting that we have people of all different types of weights who are, well, I'm not saying all different types, but at least four different types of weights go to people who have blue eyes, whereas people who have brown eyes tend to have weights of 1.9. And in fact, if you don't believe me, then I invite you to go back to the data set and actually look over the data. And you'll see that the people who have brown eyes tend to be 1.9, 0.9, 1.9, and then there's another 1.9. So there's four brown tags here, and the heights are 1.9. And you can see that in a flash by looking at this data here. Looking at your edge, and then looking at your plot. Whereas for the blue, you can see that those numbers for the height kind of skip around. Anyway, I think you get the point. I'm not going to spend too much time kind of deliberating over this, but the whole point of that was that you can look at your data, you can look at your code, and kind of you can use this code here to do other more interesting types of analyses. Now, the next thing I want to talk about with you is called the p-values. There's a lot of other statistics that sadly we don't cover in this course. Primarily, this is not a statistics course, but rather this is an analytics course. But there are certain types of statistics that I think you should know about when you're working in data science. And so these are the big ones. But I'm not saying to forget everything you've learned before about statistics, but I want to talk about the p-values though, because these really are big pieces. A lot of the models that we're working with actually use p-values. And I think the best way of describing how p-values work is to tell a story about how they're used. So imagine, for instance, that we are some kind of a drink company where we are selling drinks which are green or they are purple. So we have two different kinds of drinks that we sell. And somebody comes to us and they say that they believe, although they're not sure, but they believe that there's something wrong with the machine that's bottling the drinks. In other words, that our machine that's bottling the green drinks is filling them up higher than the machine that bottles the purple drinks. In other words, our purple drinks just don't seem to be, or the bottles just don't seem to be as full as the green bottles. And so we think, okay, well, maybe there's a problem with our machine. So what we do is we have to run a test. Now, we run a test because we have 100,000 bottles coming through our facility every day. That's a lot. We can't actually, visit each of those 1,000 or each of those 10,000, 100,000 bottles. We can't visit each of those 100,000 bottles and actually measure the amount of drink because that would just take too long. And so what we do is we use statistics. And remember what the whole notion of statistics is, and that is that we are looking at a small group of the bigger group, And we study that small group, which is actually within our computational grasp and everything. And whatever we determine from that smaller group, we extrapolate to the rest of the group, saying, this must be what we found. This must be what's going on here. So in this case here, we can't check all 100,000 bottles to see whether the green is, if we have more green liquid than purple liquid. And so what we do in this case is we select only 9 bottles randomly from our base. Now, this is 9 is really not enough, but for the sake of the example, this should be good enough. In a case like this, you might select 500 bottles, something that's actually quite a big number. But 9 bottles is just enough for our example. So we select 9 bottles randomly from our larger set. This is our superset, and this is our sample set. And so now we're going to look at those 9 bottles, and we're going to say that if we find any difference between the amount of green liquid and the amount of purple liquid, if there's any difference that exists in that sample set, then we're going to say that that difference must also present itself in these 100,000 bottles that we. So we're suggesting now we have to kind of create we have to like formalize our work here. But we're suggesting that there is something wrong with the filling of these bottles. It's always very important when you come up with the actual question that you're working with. Actually write it down and come up with an actual question that you're going after. And so we're saying that we inspected these things. We believe that the purple bottles are underfilled and the green bottles are overfilled. Or maybe the green bottles are filled correctly, whereas the purple bottles are underfilled. Either way, we're suggesting that the purple bottles have less liquid in them than the green bottles. So we ask ourselves, how can we actually check to see whether one thing is overfilled and the other thing is underfilled? And so we can use a statistical test. And in our test here, I'll tell you about the test in just a moment here, but we're working with a t-test, but we have to come up with 2 hypotheses in our t-test. And the first one, called H naught, or H sub O, if you will, or the null hypothesis. I'll just call it the null hypothesis. But we have to come up with 2 different types of questions, or two different eventualities of our analysis. The one eventuality, which is called the null hypothesis, says that there's nothing going on, that the bottles are all filled exactly the same. There's no difference between the amount of green liquid and the amount of purple liquid. It's all the same. So that's the null hypothesis, that there is nothing happening. There's nothing wrong with the machine. It's just the person who looked at these bottles initially, they didn't. They may have just seen the wrong bottles, but in general, nothing's happening. So that's our null hypothesis. Null for nothing. Nothing going on. But then we have an alternative hypothesis, that there is something happening, that our bottles are filled differently, that we do have more green liquid than we have purple liquid. There's something happening. Now, when I say there is a difference, or that there is something happening, remember, this is just analysis. It doesn't tell us where the problem is. It just says that the bottles are not the same. So we need to keep that in mind. It doesn't answer the entire question about what's going on. It just says that there is a difference. Okay, so now we're going to talk about we have our null hypothesis. So now we have to kind of figure out how we're supposed to actually work with this test. Another thing I should talk about is, remember, we only have 9 bottles from a superset of 100,000 bottles. And so this is important because you might run this test several times. For this reason, you might design a function, for instance, that runs this test for you. So you just have to select some different data sets, or you come up with a different data set, and then you run the same test over and over and over again. And the idea is that you, after you've run enough tests, then you should eventually be satisfied that you've actually figured out whether there is a difference between the amount of bottles that or the liquids that you have. So we're using these statistics to extrapolate. So one thing we do have to talk about, though, and that is that we are selecting 9 bottles. Okay, we went into the back room and we just selected 9 bottles. But remember that we are people and we have inherent biases in ourselves. And maybe, for instance, we only took the bottles that were in the front, and there are bottles in the back that we couldn't get to in the back of the room that were enclosed boxes or something, so we couldn't get those. And so we have to ask ourselves, did our sample size actually tell us the truth? And that's why you might want to run this again, where again you're choosing truly random bottles. But we're showing that we're trying to figure out whether did we correctly select our bottles here? Did something happen perhaps where we got the wrong? We chose bottles, for instance, which just happened to have different levels like this, so that we just see that, for instance, when we selected them, these are the ones that actually have the most noticeable differences. But actually, in truth, everybody is more or less, or all bottles are more or less kind of like the same. So we're going to use p-values, and p-values answer the question. They answer the two questions that we came up with here, the null hypothesis and the alternative hypothesis. That's how we answer this question. We're saying, is there anything going on, or is there nothing going on? So the p-value is actually that statistical score that we get. So we're now going to talk about where p-values, or how to use the p-value. We'll talk about how to calculate them in a second. But here, the p-value is the way that we answer the question about the null hypothesis and the alternative hypothesis. And the idea here is that when p is a very small number, most important piece here, if we forget all this stuff over here, when p is a very small number, that means if this is if below where I am right now, if below that, that's our number line between 0 and 1.5. If p is found, when we calculate this value, if it's found between 0 and 1.5, then we reject null hypothesis. Remember, the null hypothesis says there's nothing going on here. It's all fine. Nothing unusual. But we are rejecting that notion where we're saying it's not all fine here. There is some crazy stuff going on here. Something is impacting the differences in our bottles. And that is when our value of p is less than 0.05. That's if we're talking about the 95% confidence range interval, which means that I am 95% sure that that my values here, or my bottles, are actually showing some difference in how they're being filled. Now you can always have this by the way, this number here, 0.05, they call the alpha value. But you can even have a smaller number, 0.01, which means that you are 99% sure. If my value of p is less than 0.01, I'll say that I am 99% sure that there is something going on between the fillings of my bottles, so that I'm getting more green and less purple. There's something happening. I don't know what it is, but there is something happening. So remember, though, that when your p-value fits inside this range here between the 0 and the 1.05, or if it's 0 and 0.1, if it's a very small value of p for these tests, then it suggests that you throw away your null hypothesis and you conclude that there is something happening. That's what it means to reject the null hypothesis. I mean, you can always think of the null hypothesis as like kind of like null for nothing. I reject the notion that nothing is happening, or something's happening. So we talk about running a t-test here. So this is the actual statistical test. I wanted to take you through this in R. We're not actually going to be computing this in here. We're not actually going to be computing this with pen and paper, but we'll have the software do this for us, which I think you'll find is easier. So I'm going back here, going back there to my code. Oops. And let me go down here, and I'll put my T. I'll just paste everything in there, and when I run it, of course, the code doesn't look very nice, but it's called data drinks. I guess I could have used a different name for this because this seems a little bit absurd. But it's this one right here, data drinks. And so when you run this, by the way, this plot has nothing to do with this data. I always suggest throwing away these old plots when you've seen them, because if you change the data set, then you're going to look at the plot and think, oh, wow, that's my data. But actually, that's not your data. That's something else. Anyhow, so we have this. We have the color. We have the percent full. These are the 9 bottles that we chose as our random sample. And so the next thing we need to do is to run our statistical test. And our statistical test is incredibly easy. So what we're going to do now is we're going to, we have to first of all do some work here where we're going to take the data drinks data that we've just created here. And then we're going to select the color and the percent full. Now, the reason why we do that is because otherwise there's other data mixed in with our numbers here. And so come back with me to R, there we go. And so I'm going to remove the notion of observation. I don't need observation here. So what I'm going to do is I'm going to create a new data set, data drinks, which will write over, actually I'll call this data. When I run this, if I close this down and I go back to my data drinks again, you'll see that now my data has been wrangled. It's been refined. Now, normally what I would suggest is I wouldn't suggest that you write over the original data set that you have, but since we have we've taken this code, we already have this information in our code, then that means that we can go ahead and write over that if we want, because if we wanted to get back to this data set, then we could. It's right here. But now what I'm doing is so that I don't have all this extra stuff like hanging out in global environment, I'm just going to write over that original set. So for instance, you can always check your data. I can view data drinks, and if I run this, you can see that the observation is now back because I just ran this code. But now if I want to get rid of that, again, run this, and you can see now that I've just trimmed out that other blank where I'm talking about the observation number. Sometimes you'll find that the data that you get online really has nothing to do with what you need, so you can get rid of it. So now going back to our slides, that was your wrangling. I put that in there. You're probably thinking, why would I give you data that has observation in there? I want you to know that you can trim this stuff out. Right? Just take any data set, and you now have the code and the skill to pull out exactly what you need to make your analysis soar. Now, the next thing is this t-test is actually incredibly simple. Like you don't have to spend any time at all wondering what the p-value is, because you just run this code here. And so I'll run it and show you what it looks like. So here we have this. If I run this, I get this value down here. So I have what's called the Welch's 2-sample t-test, where I have some other information here. I have the t-value, the degrees of freedom. These, by the way, this is what you'd use if you're looking up a value in a table, or a t-table, your degrees of freedom, and then you have your t-value, or the score that comes out of the math, and then your table will tell you what your p-value is. But luckily, though, for us, we're using our statistic where it knows what's on that table, and so it gives us this value here called the p-value, p. So this number is p-value is equal to 0.007. That's a number which is smaller than 0.05. It's a smaller number. It's also smaller than 0.01. It's a tiny number. And so how do I make sense of that number? Well, go back over here and say, okay, well, since my p-value is fitting between my 0 and my 0.05 and my 0 and 0.01, I don't have it listed here, but because it's a small number, I'm going to reject the nothing null hypothesis. I'm going to say, remember what the hypothesis was? It was saying that there's nothing happening, it's all good, everything's fine. The bottles are filled at the same levels. I'm going to reject that notion. This is suggesting to me that the bottles are not filled at the same level, that there is something inherently wrong with my bottling company, or bottling machine, because the bottles between green and purple liquids are not being filled the same way. So there is something happening. So there is what they call the alternative hypothesis, which they just add in this code for you. Of course, they don't know exactly in R, they don't know exactly what the hypothesis is, but they're saying that whatever the hypothesis were, they must have been something about whether the values are all the same or whether they're all different. The same would be for null. The alternative one would be that they're all different. This is saying you should use the alternative hypothesis, which is actually quite nice. It used not to say that. True difference in means is not equal to 0 at 95% confidence interval, but you're really getting this idea that, for instance, the means are now different. So what this is actually doing in this t-test, I'm not sure why they call it t. I would have called it the mean test, but it's the t-test. But what it's doing is it's looking at the green means. In other words, come back with me, if you will, to the slides. It's going back to our data set, which is here. It's looking at the green bottles. It's tallying the means of those bottles. And then it also looks at the means for the purple bottles. And then it's comparing the mean from the green mean the mean green, and then the mean purple. It's looking at and it's comparing those two things here, and that comparison is there's other math that's happening there too, which you can look up if you'd like from in your statistics course. But those numbers are then being used to calculate this value here, and this p-value is saying, wait a minute, there's a difference, and I'm 99% sure the difference exists between the green and the purple. And then, in fact, you have to look down here to find out, well, which is bigger. It's saying in general, the green liquids are 99% confidence level. These are the means. 67.5, and the purple is 24.0. And so you can just look at these. You have two pieces of information to look at. You have this number here, the p-value, and then you have these two means here to look at, and then you can get an idea. So the p-value is small, so there is something happening. Therefore, I should look at these means to see which values are higher, which value is higher, and which value is lower. And this is saying that the green mean higher, which means that my bottles are being filled like this in general for my 100,000. Now, it's kind of an exciting test, if you will, because you now have the capacity or the ability to, I guess, to check many hundreds of thousands of things using a very small sample size. And you even have the idea that you're actually uncovering the truth. You know what's going on because you have this 95% confidence here. So you can say, is my sample telling the truth? I believe so, because my value is within the 95 and 99% confidence. Let's see what else is there. Oh, this is another thing that I put together. This is a function that I wanted to, this is why we actually talked about functions early on. I find if you're anything like me, then you'll probably find that when you're working on your statistics, if it's late at night, you might find, for instance, you're looking at all these p-values, and after a while, it's like you just think to yourself, wait, what values are smaller than 0.5? And that is something that just drives me absolutely berserk. So let me go and just show you something. I'm going to run my my test here. In fact, you can see what I'm working on here. I have to organize my thing here. I'm going to run my test, and then the value that I get from that test, I'm going to dump into this function that I'm writing. And this function is going to tell me, do I accept that null hypothesis or not? Because so many things going on. Okay, so I'll drop that down here. I'm trying to make this as clean as I can, just so. Okay, so this is it. So I'm really just going back and forth, making my code look like this. Just follow. Now, going back up here, I'm going to be creating a variable called myout, which is exactly the t-test variables that we came up with before. That's exactly this. That's this line here. So I'll run this, and my new variable shows up there. And then this is actually rather important here. If I show you this line, myout.p-value, I can actually isolate just the p-value for my test, 0.007, which is this value up here. So now I don't have to look at this thing anymore. I can actually just say, okay, this is the value I want, give me that. And then here I have this function called reject or what. And when I reject or what, when I run this, this function here with the value that is my p-value, then you'll see that it says, it just prints out a statement for you. It says that something is going on. Rejects the null hypothesis. It's a very simple function, but all it's doing is it says, is my p-value less than or equal to 0.05? If that's the case, then if my p-value is greater than 0.05, then accept the null hypothesis to suggest that nothing is happening. That means there's no difference between my bottles. And if that's not the case, then reject the null hypothesis. In other words, embrace the alternative hypothesis, which is saying that something is happening. So I think that, I mean, you don't have to use this function if you don't want to. But I recommend, though, that if you are working with like many different p-values and it's late at night and your eyes getting tired, then sometimes having a function like this, it just tells you, reject the null hypothesis. That actually helps greatly because then your eyes don't play tricks on you. Anyway, this is something that actually, I'll tell you something. I wrote this particular code for this t-test my out, this is actual code that I used in my own work. And so I'm hoping that it gives you as much help as it gave me. Anyway, I think going back to our slides, I think that's my last slide I want to talk about before we go into the next thing. I think that we're done with the slide deck. But if you are looking to get more practice out of this whole thing here, then please do. You can always go to your data sets that you have built into R, type in data, open and close parentheses, and you have a whole bunch of really nice data that you can use. And you just try running some t-tests on these.